Thank you so much then for the kind presentation, and also thank you for the organizers and everyone participating for the workshop for giving their time for my talk. So I'm going to talk about not that much evolutionary game theory, so sorry beforehand. I'm going to connect it to evolutionary game theory, I promise, on the last slide, but I thought that still game theory is an interest for everyone, so you might find it interesting. So what I'm going to look at is that how we can incorporate the decision-making processes of the individuals in the epidemic control problems by using a large population game approximation method, which we call mean field games. So this thing, I did my PhD during the COVID, and my PhD was about mean field games. And as you might guess, during COVID, this situation was an interest to everyone, including me. We, for example, saw that even if there were no mask mandates, people were considering whether they should wear one anyway, or even if the virus was surgent, people are considering whether they should travel or not travel anyway. So we saw non-compliance in terms of overprotection or underprotection, and the interest of mine of modeling the individual behavior came from these observations. So in the classical epidemic models, I think you are much more expert than me in these things. What we have is that generally we have the system level models, such as the susceptible, infected, recovered models, or we can go to more like the agent-based models where we model the individuals directly, generally with computational methods. So these agent-based models are very good for heterogeneity and also for understanding complex things that may come out of the systems, but sometimes they lack the tractability. So we wanted to have tractability in our models following this observation. Our question was what would happen if the agents were deciding strategically? They would try to maximize some objectives of themselves. And what if they are not exactly identical and they have some heterogeneities? So following this thing, we are going to use some real-life survey data results to build some mathematical models that are going to use large population game theoretical approaches to incorporate the decision-making of the individuals and also include some heterogeneities through the multi-population settings. So in our setting, we are going to have a large population of agents, and this large population is going to actually be the limit of infinitely many players. And we are going to have a disease spreading depending on the agent's own behaviors to slow the spread. This can be social distancing and the vaccination. And the agents are not going to be cooperating. We are going to look for a Nash equilibrium where everyone is trying to maximize their own outcomes without considering the other people's outcomes. So in our agent population, what we need to do is that since we are at the interactions of agents, we need to find a Nash equilibrium. But the problem with Nash equilibrium is that when you have large number of players, especially if your models are dynamic, stochastic, continuous action possibly, it is very hard to find the Nash equilibrium. So in 2006, 2007, this mean field game methodology was proposed both in the engineering and applied math community to approximate large population differential games, so overtime games. In this methodology, what we assume is that we assume the agents are identical and infinitesimal, and they interact with each other symmetrically through some kind of population statistics. For example, in the epidemiology example, this can be the proportion of the infected agents. Then we can focus on a representative agent and this agent's interaction with the full population instead of focusing all the pair interactions. So if we want to include some heterogeneities, I'm going to explain some other ways later on too. But in the first project I'm going to mention, we can look at multi-population settings. Each population within would be homogeneous, but between the populations, we would have some heterogeneities. They can have different objective functions or different parameters. Okay? So In the outline of this, so basically what I'm going to first do is that we are going to go from the susceptible infected recovered models to individual decision-making models. After introducing this mean field game setting, we are going to look how we can use the survey results to have a mathematical model. We are going to define our Nash equilibrium in this differential setting, and we are going to discuss how we can characterize it with some differential equation system, and we are going to look at some numerical results. The main focus will be this paper, which my PhD student, Ning Liu, some graduate students from UIU, Sijun Kayang. Soren Larsen is a postdoc right now in UC Berkeley. My colleague, Pamela Martinez, who is in the microbiology department, and she's the one actually who conducted this survey and told me about that there are some heterogeneous behaviors in the societies. So I was more like the math side of it, and she is the one giving the motivation for the heterogeneities. I put some related work, as you see, like I started it like in the past around COVID, and now like I'm going back to this application again, and I'm more interested in more like real life applications of it. So susceptible infected recovered model, you are all familiar with it. I just wanted to introduce you for the notations. We have the transitions from susceptible to infected with the infection rate beta depending on the infected population's proportion. So this system is a population level system. We don't look at the individuals. Instead, we give the proportion of susceptible, infected, recovered at the population. What we want to do is that we want to model an individual decision making. So we can do this by going to the finite agent setting. We consider n many agents, and each agent is going to be in a health status, susceptible, infected, recovered. Then if we assume that the meetings are going to occur random with the rate beta, and then we can basically model this individual's problem with a continuous time Markov chain. So this is not discrete time, continuous time, which means that an agent jumps from the susceptible to infected after an exponential distributed time with rate beta and the proportion of infected. So at this level, I don't have any decision of the individuals, but I want to add the decision making. So I need to add some type of controls. So these controls are going to be socialization level and the vaccination. And we want the probability of the infection to be decreased by the social distancing of two agents that are meeting in a multiplicative way. So we want to have a setting where the infected people are sitting at home. Even if the susceptible people are outside, they are not going to get infected. But if the susceptible people are staying at home, even the infected people are outside and enjoying their life, they are not going to get infected. So this requires us to have some multiplicative effects. And we introduce our controls. So then we add our controls here. This is now the continuous time Markov chain for the state jumps of the agent I. Okay, as you see, this is a socialization level of the agent I. It affects his transition. It will be something between 0, 1. If it is lower, it will be a lower rate, so it will take more time to jump to I. As well as we see that it is getting affected by the other infected agent socialization levels. This K here, this here means that the Kate agent is infected, and we take that Kate agent into socialization level in the transition rate. We also have an interaction level between the agent I and K that we can change depending on how the populations interact with each other. Okay, so this is a finite setting. We have the vaccination decision here. Vaccination decision only depends on agent I. There are no multiplicative interactions there with the other agents. Okay. So then, after this finite setting, we wanted to go and understand how people behave, okay? And this part was thanks to Pamela's input and her survey. We looked at the survey results. The survey was asking some behavioral questions to the individuals in Illinois. One of the questions was, for example, have you changed your behavior? For example, mask wearing or reducing contact in response to your concern to COVID-19. So what we saw is that there were like socioeconomic status level type of differences in the behavior, but there was also differences in the authority perception. If people were more willing to follow the authority, they were more likely to change their behavior. But if they weren't willing to follow the authority, then they didn't want to change their behavior. They wanted to keep their socialization level as before. So after seeing these differences, we decided to basically stratify the population into 6 groups. We have the low-income people that are indifferent to the authority. Then we have the middle-income follower of the authority. So the first one, L, M, and H, gives the low, middle, high income. The I and the F gives the indifference to authority and the followers to the authority. So after this, what we need to do is that now, as I said, finding a niche equilibrium tractably, like in a mathematical way, is very hard if we have large number of players. So we go to the mean field limit. What happens is that in our dynamics, now we can focus on a representative agent in a specific population. Let's say that I am looking at the representative player in population K. This person's continuous time Markov chain is going to be the limit of the continuous time Markov chain I introduce. I introduce here the variable Z. This is the weighted socialization level of the infected people. So we just go to the limit. The other thing we need to do is that we need to write the objectives for the individuals. So we assume that public health authority is setting some social distancing guidelines that we are going to show with lambda S, lambda I, lambda R for susceptible, infected, and recovered people. If it is 1, they say don't do any like restriction. You continue your life as you want. If it is 0, you stay home and you shouldn't do anything. But our people don't need to follow this, don't have to follow this. We are going to have common objectives. They are going to try to minimize their infection costs and the social vaccination costs. But the followers, the authority followers, they want to stay close to these guidelines, but the indifference want to stay close to the regular socialization levels, which is 1 for the susceptible and recovered people, and something a little bit lower than 1 for the infected people, because all of us, without any authority perception, we want to stay at home when we are sick. So then, mathematically, how we can write this? We have a dynamical problem between time 0 and t. If the people are followers, they want to stay close to the guideline. If they are indifferent, they want to stay close to the 1 level. They have a vaccination cost and an infection cost. Okay? So as you see, the objectives are going to be the same with respect to the socioeconomic status. Of course, the parameter levels can be different, because it might be more costly to get infection for the lower socioeconomic status individuals. But in terms of the form, the followers and the indifference are going to differ in terms of the deviation cost. So how can we define the equilibrium and characterize it? We are going to find a multi-population mean field game niche equilibrium. This is like a regular niche equilibrium where no one has a profitable deviation from their behavior while keeping the others the same. Okay, so we are in a stable case where no one can find any profitable deviation. They want to keep their vaccination and socialization level behavior over time basically the same. Okay, so here, like I put a lot of equations. I just wanted to mention you how we can characterize these type of things. I'm not going to go into too much detail, but what we do is that we are going to use some like ideas from stochastic optimal control and some ideas from basically game theory, and we are going to characterize the solution, which means that if we solve this system, we can find the equilibrium controls by using some forward and backward differential equations. The forward ones are going to give us the dynamics of the susceptible, infected, and recovered in each population K. And the backward ones are going to give us something called value function, which is the expected minimized cost at that time if you start from a specific state. Okay, so for example, this is the dynamics of the value function, expected minimized cost of the recovered people over the time. Okay. So if we solve this for forward-backward ordinary differential equation system, we can plot this P and U's here, and we can find equilibrium socialization and vaccination levels. As you see, the infected and recovered people are going to follow the guidelines or follow what they wanted to do if they are indifferent, but the susceptible people can deviate from them. So theoretically, characterization of that equilibrium is one theorem. The second one would be whether there exists a solution, and we show that there exists a unique solution to this system. So then our next step would be to go to the numerical experiments. So the numerical experiments here, again, thanks to Pamela's nice survey, we try to parameterize our model. So most of the things, for example, recovery rate or the waning of immunity rate, following the papers, we chose them not group dependent because we assume that without the SES or without the authority perception, the recovery time from the COVID is on average 7 days, okay? So the parts that we had the differences is, for example, cost of treatment, cost of infection, and the cost of vaccination. We saw that following which of the following statements describes the main reasons you did not receive medical care. We looked at the costs of infection people had. And we saw that there is a difference between the socioeconomic status. So if they are low SES, they are going to have a higher infection cost. The other thing is the vaccination. So vaccination, we treat it as a perceived vaccination cost. So if this socioeconomic status was lower, it was a higher vaccination cost due to the monetary reasons. But also if they were the public health authority or like authority followers, it was also a higher cost to get vaccinated. They saw more like reasons not to get vaccinated according to the survey results. So following this thing, we decided to compare the results of 3 types of guidelines. One of them is the permissive. So the public health authority tells just like 0.9 level, a little bit caution for everyone, susceptible, infected, and recovered. The second one is infected. We keep susceptible and recovered the same level, but we put a more restrictive guideline for the infected people at the level of 0.6. And the strict one, we put for susceptible, infected, and recovered stricter guidelines. The first experiment we did was to compare the permissive guidelines where everyone was given like relaxed guidelines, and the adaptive one where the infected people were given more strict guidelines. So what we saw was first, we saw a free rider behavior of susceptibles. This is a socialization level chosen by the susceptible people. Since the time is a little bit restrictive, I'm not going to go into too much detail. But what we do is that we are, for example, comparing the solid lines to the dashed lines here. The dashed one is the adaptive one. And we see the socialization is getting higher when there are adaptive guidelines. This is a free rider effect for the susceptibles because the infected people are following the guidelines, especially the followers. So at the end, the susceptible people can socialize more, okay? This is the proportion of the infected. As expected, with the dashed lines, you see that the proportion of infected will be less because we have more strict guidelines. And we say that the vaccination levels has some trade-off. Now they are going to be lower, but in terms of the group differences, the ordering doesn't change. The other one is the permissive versus the strict one. We see again, as expected, the proportion of infected should be decreasing. But the interesting thing is that now we see a free rider behavior of indifferent susceptibles. Followers are also trying to follow the more stricter guidelines. So the follower people, susceptible people are decreasing their behavior. But when we look at the red ones, we see that the dash dotted ones, which is a strict one, people are increasing their socialization by taking advantage of the protective behavior of the others. The interesting thing is that since these people are now socially distancing more, they are thinking vaccination is not that required, so they are getting vaccinated less, okay? So we see that there are some trade-offs in the socialization and vaccination. This is a little bit obvious. So as the guidelines become stricter, infection peaks are going to be delayed and they are going to be lower. It's just like a sanity check. In the last 30 seconds, I want to mention some other directions we can go. Mean-field games have a very strict idea of like you need to have identical people, you need to like interact with people symmetrically, but you can relax these things. For example, we went to the multi-population setting, or you can put a full network that we present with something called growth function, which is the limit of the networks. Or you can try to look at the public health authority's problem on top of the decision-making of the individuals. And this is called Stackelberg equilibrium, where the public health authority also does some optimization of the policies. So as you saw, like in this mathematical model, even if it is a toy model, even if it is like mathematically a little bit involved, what we try to do is that we try to use the survey data to make it a little bit realistic. And we show that there is a free rider behavior and some trade-offs between the socialization and the vaccination. For the future, what we are interested in is that we want to put the altruism and collaboration in these models. A lot of people are interested in the evolution of the collaboration. I think like having some collaboration aspect would be interesting. Also, another thing, as I mentioned, like I'm going to mention evolutionary game theory in the last slide. Actually, with Dan, we are collaborating on a project where we have generations of different types of people evolving, and each generation is modeled as a mean-field game instead of a static game with a payoff matrix. So thank you very much for listening, and if you have any questions, I'll be happy to answer later. Yes.
For one question, that's very exciting.
When you showed the forward backward ODEs, what were the final values for the set that you solved?
Yeah, very good question. It should be the terminal cost. Since we didn't have any terminal cost, only running cost, it is 0.
Okay.
So it should be normally the cost at time t, so it should be the terminal cost, but we didn't have a terminal cost.
So does that include an assumption that eventually the epidemic passes and then we return back to like a...
So it's like we are here assuming that we are only doing one episode, so you can like if it is flu, it is only this winter's thing. And at the terminal time, we are not getting any cost or any stimulus check, etc. Like for example, I had some other things, and our terminal cost was a stimulus check, which was a reward because at COVID we had stimulus check, right?